As our next speaker and last in this morning section of the Granville Fest, we have Mike Bennett from University of British Columbia, who will speak to us about perfect powers in progression and variance.
Are we on here? Okay, well, I'd like to thank the organizers for the kind invitation. I'm honored and very happy to be here. This thing's celebrating Andrew's 60th birthday. It's hard to believe. If you're 60, we first met a long time ago. I think I was a grad student and you were maybe a starting postdoc with John Friedlander, something like that, and then have kept in touch over the years. Remember a few incidents. One of them, I think Eunice mentioned the other day, this is from 1994, I believe, 1995. So this is Andrew on the summit of Mount Toubkal in Morocco, the highest mountain in North Africa. And what's amazing to me is that he looks kind of exactly the same. The glasses are different. And, you know, I'm trying to, I think it's kind of that you're remarkably well preserved, or it's a sort of Schnitzel thing where you've been the same age for a definite period of time. It wasn't 60 anyway. And just one more of that, because it's sort of the Clint Eastwood kind of thing with Andrew riding into some town to save the people from persecution by a bandit gang. Anyway, I'd like to, this will be a light talk compared to some you'll get in this thing, and I'd like to apologize. This is not joint work with James Maynard. There'll be, but he just won't work with me. So I'd like to start. It's one of these things. I mean, my talks are always kind of the same formula. You know, I start with an unmotivated problem, transform it into an uninteresting Diophantine equation, and then fail to solve it. So that's sort of what's going to happen here. So, but I'll start with something we do kind of know. So it's one of these things that if you take a polynomial under mild constraints, so not degree 1, then the sort of set of perfect powers, sort of when you substitute integral variables here, it's finite, and this is actually, there's a lot of sort of big machinery underneath this, and it's a beautiful result. So if you fix the exponent L, then this is essentially follows from Siegel's theorem as proved by Levesque back in the 50s. But now if you even make L a variable, then we have a finiteness result under sort of mild conditions on the exponent, and that follows from work of Schinzel and Tiedemann, and it's really coming from using bounds for linear forms and logarithms. So pretty heavy results from Diophantine approximation gets you this. Now, I'm sort of interested in the cases where you can really solve this, and you think, well, this is kind of solved. It's effective. You can write down a bound upon the x, the z, and the L just in terms of the coefficients and degree of the polynomial. So, but what's arguably interesting is that if you go sort of the next step up and you just make the thing a binary form, then suddenly all bets are off. We really have finiteness results in only a handful of cases. And, you know, sort of to illustrate that again, if you take a pretty simple looking polynomial, this is essentially Fermat's last theorem, is to do this game with x, y, x plus y. So you get the sense that it's not going to be that easy, and that in general, you can't really do this for too many things. There's some binary forms. So x squared plus y to the 4th, not a binary form, but we heard that mentioned before. It gets its primes. You can also handle when that's an nth power. It's essentially work of Jordan-Ellenberg. So what's maybe interesting is that I go back to the previous problem. It's a solved problem, but really, if you write down your favorite polynomial, the odds are pretty good that you can't actually solve it. You can get bounds, but they're going to be terrible. And so to illustrate that, you know, the polynomial x squared minus 2, we can't solve this equation. I mean, we can in an engineering sense that the solutions all have x plus or minus 1, but nonetheless, we can't actually say that's the case. We can bound everything else. We can bound, it's going to be an nth power, then that exponent on L is bounded by something like 1,000. So it's pretty small. But to actually solve it, it's beyond current technology. It's a frustrating situation. I don't like working hard on things like this, so let's try to find some class of polynomials where you really can solve it easily. And that usually means they're polynomials where you don't have to rely upon linear forms and logs. There's other techniques that can help. So a sort of classic example of that would be polynomials got by taking products of consecutive integers. So this is actually, this goes back to a conjecture of Liouville from the 1850s about when products of consecutive positive integers could be a perfect power. So Liouville conjectured it couldn't happen. And this, you could make an argument, this is the problem that Erdos might have worked on the longest, because he has published papers on this from the 30s, and many of them, and they carry on, and he finished it in 1975 with John Selfridge. So he showed that, in fact, there are no perfect powers here. And what's interesting is that people were using a lot of machinery from Diophantine approximation to attack the problem, but the actual solution is from graph theory, which is kind of a neat result. So it's a sort of neat thing that you get away from the heavy machinery Diophantine approximation and solve it in a way which is very elegantly, I guess, finds the solutions to f of x equals z to the L for a whole family of polynomials f. And so what I want to talk about today are sort of generalizations of this and degrees to which I'm trying to weaken the hypotheses. Obviously, when we have all these consecutive integers, it can work. And the question you might ask is, well, how flexible is this? Can we delete terms? Can we modify this in some ways and still get a nice solution? So yeah, there are many papers attacking along these lines, where instead of having all the integers, you say, well, let's delete some. How many can we delete and still have the graph theory sort of take us to the finish line? And there's different ways to quantify this, but the takeaway, if you want and probably should ignore some of these bounds, the takeaway is that you can eliminate a positive proportion of the k consecutive integers and still get a nice result. So, but it really is sort of a positive proportion. Okay. And again, the techniques here, this is a combination of some of the arguments used by Erdos with bounds for linear forms of logs, and actually something called the hypergeometric method. So other techniques from Diophantine approximation. There's quite a lot goes into this result of Nesterenko and Shorey. And this is, again, the culmination of a long series of papers by Tarlak Shorey. So in another direction, and this is something Erdos again looked at, was you can ask the question of, so instead of having consecutive integers, let's have consecutive integers in a progression. And this apparently makes the problem much harder. But so it's progression, and I have some constraints. We're going to make, so the modulus of the progression here is y. We'll assume x and y are co-prime, and we exclude this pair here. And these are sort of necessary assumptions. You have infinitely many solutions ranging from trivial to apparently less trivial in both of these cases. And so what I want to talk about are sort of these two equations I label here 1 and 2 and variance therein. So 1, I'm gonna look at this thing in progressions, and this one looks like the first equation we dealt with, but it's here I'm going to think about x being rational. So instead of integer solutions, we'll look at rational solutions, and it's not very hard to show that really 2 is a special case of 1, and it's a special case of 1 where the modulus y is actually an nth power. So 2 is much, so rational solutions to equation 2 are much easier than integer solutions to equation. In the case of equation 2, I'll come back to that in a bit. Samir Siksak and I showed that for a fixed k, it's a finite problem. This is unfortunate. I mean, in Erdős's result, it's all k at once. It's not just finite. There are no solutions. That's what you'd love to show. It's probably true for k bigger than or equal to something like 4, but it's an open problem. So we've kind of solved that. And then if we move back to the more general thing, we actually have a conjecture of Erdos. I mean, that doesn't really narrow it down. It's like a theorem of Erdos or a conjecture of Erdos. He had a few. Is that in fact, there are no solutions at all if k is large enough. In fairness, I've seen this called a conjecture of Erdos in about 30 different papers. It's not clear Erdos ever conjectured this. He might have. He didn't in print. I went through 1,500 and something papers and looked for it, and he never did. He could have done it at a conference, or who knows. But enough people have called it that, and he's unlikely to dispute it. So we'll call it that. Nonetheless, there's this conjecture. Okay, and what can you actually show? So if you look at this thing, and again, I've got assumptions that k and l aren't 3, 2, and that x and y are relatively prime. So there are many papers on this problem for what it's worth. So you can show you have finitely many solutions. That's in all the variables. If y is fixed, so that's a straight generalization of the case y equals 1, the Erdos Selfridge thing, using similar arguments. So I mark select. If L and the number of prime factors of y are fixed, if L and K are fixed, and that's a state in a nice paper of a much younger Andrew and Henri, an even younger Henri, from 1995, and this is a part of a truly beautiful paper where Andrew and Henri prove the finiteness for the generalized Fermat equation. If you have x to the p plus y to the q equals z to the r, where the sum of the reciprocals is less than 1. So that's a beautiful result. I remember discussing that I think we'd each had somewhere around that time some paper written which you'd submitted to some journal, and they rejected and said, but this is obvious, which it very much isn't if you look at it. And then this, I think, is your most cited paper. It's been cited hundreds of times, but it was rejected with a really silly referee's report. And you know who you are if you're in the room. And then here's a strange, so there's actually an earlier paper I had with Niels Bruin and a couple others where we prove finiteness for fixed k up to 84. And then I came up with a new idea to push it up to the exciting number 15,177. It could go further, but possibly not much further. There's a lot of computation things involved here, and you have to do lots of stuff about the thinness of sets with 3-term arithmetic progressions in it to get this result. And then more recently still, I have a paper with Samir Siksak where we prove it's finite if k is large and fixed. And this takes a surprising amount of work. And large, I've never admitted how large is. You think, gosh, you've got it up to 15,177. That's pretty large. You can just compute and fill the gap. But large is probably 10 to the 10 to the million sort of thing. So quite large. Okay. And again, as noted earlier, the conjecture is that there's none at all. So we're saying finitely many, if you like, for fixed k, there should be none at all for k greater than or equal to k, some k0. K0 is probably 4, not 10 to the 10 to the million. So what I want to look at, the last bit, is again, sort of the analog of this. For these two problems, where either we're looking for rational solutions to 3 or integral solutions, co-prime solutions to 4, where instead of having all the integers from 1 to k, or if you prefer 0 to k minus 1, I'll have t of them. They're distinct where t is smaller than k. And ask, okay, where does it break down? And so it's more, I guess this is all part of I'm trying to understand the arguments. The arguments is sort of, it's easier in these cases, and the arguments, they're slightly malleable, but at some point it all fails. And so how much can you, it's one of these sort of games of, what's the one, you Jenga, where you keep pulling, I'll take a term out, I'll take another term out, and at some point it collapses and the argument completely fails. So that's sort of me trying to understand these things. Okay. And so again, to emphasize that in this case as well, of course, 3 with rational is a very special case of 2. But 3 is where there are results. So there are no results in the literature. For 4, there are maybe 3 or 4 papers in the last couple of years for question 3. So here's a result for question 3 that's published. So it's Samuel Edis published a paper that said, okay, so before we could take out in the general problem integer solutions, for product of consecutive integers, you could take out sort of greater than k of them. You could throw away a positive proportion and still pull the argument through. Here it's much smaller. So here we're removing root k over log k of them. So not very many in some sense, and still getting finiteness. And again, you could make it quite explicit here. So, and I'll show you the proof, and this is the sort of the proof, Samir and I proof in general. If you remove none of them, it's kind of the same proof, except that you have to leave enough to make it work. So the idea, of course, is that if you have a product of these, so here I'm actually written this, so these are integers, so it doesn't quite look like what I had before. But so here again, the case of rational things, product being an nth power, is equivalent to the sort of integer arithmetic progression, where the progression modulus is itself an nth power. So it's something like this. I've got a product of these things, or maybe some of these things, but this thing is supposed to, the product of these is supposed to be z to the L, where here these are all integers. And so in particular, up to primes bounded by k, each of these things is individually an nth power. So these things are all nth powers. And so the idea, of course, if I have k consecutive terms in a progression, and you pick a prime, smaller than k, say, then it will divide one of them or more of them. Or it'll divide the modulus of the progression. So that's what we get. So in particular, if I take a prime that's between k over 2 and k, say, it will divide one of these terms, two of these terms, or none of these terms. Okay, that's a triviality, but in case it divides none of these terms, it divides y. So there's really three cases. Let's suppose, just for the sake of this argument, we're in the first case where it divides two of them. And let's suppose it divides these two. Then you can just write down this little, just comes from a very simple polynomial identity. You could write down this and well, this doesn't look very helpful, except that this bit's basically an nth power. This bit's basically an nth power. Same with that, same with that, same with that. And so what that gives you is one of these ternary Diophantine equations, signature, if you like, LLL, with the property that, well, the coefficients, I don't know what they are, but they're greatest prime divisors at most k. And then, well, what's happened if we go back into this? So remember, I've packed all of the p's into this term and this term. And the product is supposed to be an nth power. So the number of p's I've packed in is congruent to 0 mod L. So that all gets swallowed up into one of the into xyz. So what I've got here is a ternary equation where the p, the particular p, doesn't divide the coefficients, but it does divide the xyz. So when you write down a Frey curve corresponding Frey-Elgwar's curve to this ternary equation, it has the property that the Frey curve has Babb reduction at p, but what you hit after level lowering doesn't. It goes away. So you ribbit level lowering says we're going to level lower mod L, and we've got some 0 mod L contribution from p, so that goes away. And so you get Babb reduction at p, good reduction at p, and when you put these congruences together, it tells you that something here is congruent to something it's not equal to mod L, and that bounds L. So that's sort of a little trick they play in this game. So it bounds L, and it doesn't bound L very well. It bounds L, but like e to the 3 to the k. But the point is, it bounds L. We fix k, and so L is bounded, so we can now appeal to the result of Andrew and Henri to say there's finitely many solutions, because each one of them is a finite problem. And so that was a situation where we omitted nothing, okay, where we had all of these terms. Okay, well, then we could get this identity. And so we can do similar identities. These are this is if k was a prime p, pardon me, was between k over 2 and k. We can do similar, somewhat more complicated identities if the primes between k over 3 and k over 2. Okay, and similar identities if the prime divides only one of these terms. So those are all great. And so all we have to do is make sure that we've got some prime in the right interval that isn't in all these omitted terms. So the question is, how many can we omit to guarantee that we've got a prime between k over 3 and k over 2, say? This is not the identity I showed you, slightly different. But, well, if I omitted both of these indices, then the difference here, p, has to be in this different set. So if these are the omitted terms. And we know how many differences we can have. It's basically just quadratic in the number of terms. And so the number of primes between k over 3 and k over 2 is greater than k over log k. And so this allows us to omit root k over log k terms. It's a very straightforward argument. You seem dubious, sir. Okay, I'll have to think of a way to avoid it. Okay. All right. And so if we go back to the more general equation where we're assuming that the modulus of progression is not an nth power, then again, for say a prime in the interval k over 2, okay, we have sort of four terms, four possibilities. We either divide two of them, one of them, somehow the indices got omitted, or the prime divided the modulus of the progression. And in this simpler case where that progression was an nth power, this thing here turned out not to be a problem. Here it's where all the work goes. Okay, so in the first two cases, things are very easy. So you're done there. So what happens is that in the case where you divide the modulus of the progression, you don't get a contradiction this way, but you end up with a situation where the thing lets you get, so here's t is the total number of terms. We're assuming it's close to k. We end up with a lot of different Frey curves we can play around with. And for each of these, we have some arithmetic information. And so what we get is a lot of different curves, which have the property that they look like they have CM. So this is morally what goes on. There's a lot. This is where the heavy lifting, the analytic number theory comes in, because at the end of the day, there's different ways to attack this. So my original attack from many, many years ago was to say, well, there's just too many super singular primes. So look at the primes that are 3 mod 4. This is basically saying that they're always 0 for this thing. So it's this large collection, so of cubic in L, collection of elliptic curves, cubic in T, pardon me, that have the property that they don't have CM. You can show that, but they're pretending to far too often. And so you can use Chepatarov to say, as long as the conductor's not too big, that you can get a contradiction out of it. That's morally what's going on, but that's not how the argument actually works, because that didn't work. It's too hard. And I think you have to assume GRH. But nonetheless, I will put that's the entire paper with Samir in one line. With much work, we get a contradiction from this. Okay, so this, I thought I'd better state a result of some sort. The result is that we can basically get the same order of terms omitted as we could for just the rational case. So if you like, this is the case for products of terms in progression. And if the progression modulus was itself an nth power, you can omit root k over log k. And I'm saying is that with a certain amount of work and worst constants, you can do the same in a more general case. So again, the worst constants, they're effectively computable positive absolute constants, C0 and K0. It's one of these situations that C0 turns out to be incredibly small and K0 turns out to be incredibly large, and it'd be much nicer if it was the other way around, yes, as far as I can tell. Just, I think, a last slide just to say there are some other new ingredients besides just turning the crank. One has to actually work quite carefully here with small primes and playing off split versus non-split multiplicative reduction, because you can actually determine for your Frey curve which it is, and that in some sense is preserved under level lowering. So you get to play this off, and that can give you some purchase. Using primes that are not actually showing up, that are actually primes good reduction, and using the fact that, of course, we're dealing with all these ternary equations, but we have more because we have an arithmetic progression. And so we know that any prime, whether it is sort of in the picture or not, has to divide, p consecutive terms in this progression or the modulus. And so we have extra arithmetic information that has not typically been used before. And then just, being careful. But I should add that the interesting thing, so for this paper with Samir, we had, very detailed sort of argument using sort of short character sums and things like this. And then Andrew came along and said, you don't know what you're talking about, which is fair. You can do this argument much more cleanly. And he just gave this beautiful, clean argument, which I think we have an appendix in this paper. And at the time, it was like, oh, that's just a nicer, cleaner argument. But it turns out for these applications, it's just a better argument. It gives better constants, so it gives you more wiggle room to omit things. Our original thing would give even worse constants, K0 and C0. With Andrew's help, it's not quite so bad, though in point of fact, I never worked it out quite technically. But, right. Thank you very much. Happy birthday, Andrew.
Thank you, Mike. Are there questions?
Be careful, I have other pictures.
No, so you reduce to this not particularly sparse subset of 1 through k, and then you use very weak bound.
Yeah.
But if you attain the bound, there may be structure to exploit. So it seems like it's time to introduce additive combinatorics to.
Yeah, I think it's morally certain that you can do better if you knew what you were doing.
No, but it's just if the UIs have any structure, then you can use it, right? And if they don't have structure, then you probably can do better bounds on the number of elements. So I think that root k over log k can probably.
I think you're right, and I kind of had a feeling of a way that which should be able to get k over log k, but I didn't think. Well, I think I could stop it at that. That seems a valid statement. I didn't think.
Any more questions? Okay, if not, let us thank Mike again for a very nice talk.